So I'm going to just warn you what you're about to consume here in the next 15 minutes. I'm going to rely on a lot of maps. That's a bit of an overdose. And only a couple of photos. And if this wasn't funny, the 5% there is not accurate. Okay, and also I'm going to try to avoid making any mistakes of ignorance, but if I do, please forgive me. All right, so we're going to start with BC before we focus in on this area here. What we're looking at, this is kind of similar to what Stuart just showed, though he showed greenhouse gas emissions for these three different, and what we're looking at here is actually the temperature. So the black line there on the left, that's historical temperature, averaged over all of BC. And so, we have about 60 years of record of that. And it's wiggly. We have some years that are colder than others, some years that are warmer than others. The difference there between the coldest of the cold years and the warmest of the warm years is only a few degrees, which doesn't sound like a lot, but if you think about averaging over an entire year and averaging over the entire province, a lot of those differences are going to average out. So to be a degree or two warmer or colder than normal, it takes a lot. And so those extreme warm years there, you'll have heat waves, and the Kelowna wildfires happen during one of those warmest years there. During the coldest years in the historical record, we often have a lot of flooding on the Fraser. So a difference of a couple of degrees will have a big impact on the landscape. Going back further with oral traditions, many hundreds of years, many of the stories are about climate event, very weird years that are different from normal, much warmer or colder. Okay, so if we take those years and put them on that sort of bell curve there, with cold years and warm years, I'm going to flip that down there so we can see the sort of bell curve. We're going to follow this business as usual, this RCP 8.5, and follow that up to the end of the century there. So that bell curve at the end of the century, so that's about 6 degrees of warming for BC as a whole. That's more than global. The warming over a land area is a little bit more than globally. So about 6 degrees of warming by the end of the century compared to 1971 to 2000. That's a climate where the abnormally cold years that are so cold, weird things happen on the landscape. Those years are warmer than the extreme warmest years of the historical record. So just think back to we've had a couple of real warm years these last couple of years, these record-breaking warm years, 2015, for example. And imagine that being the extreme cold year, so strange that it causes weird things to happen. The normal years are warmer than that, and the warm years are warmer than that. So that's really a different place. We haven't had climate like that in BC for at least tens of thousands of years, perhaps millions of years. So that's the bad news. That's the red curve. This blue curve though, this is heavy greenhouse gas mitigation. This is following the Paris, what Stuart talked about, the agreements that were made in Paris. Aspirationally, we really want to have 2 degrees globally from pre-industrial. That works out to about 2 degrees for BC from 71 to 2000. Even under this, so to get there, you saw when Stuart showed the greenhouse gas emissions, you saw a deep reduction down to zero emissions within a couple of decades from now, and then staying at zero, net zero, in fact, sucking carbon out of the atmosphere. So that's pretty optimistic, pretty aggressive, and to get to that, we're still going to need to adapt to climate change. So even in this most successful scenario, you can see that the new normal fall under that blue line is still comparable to the warmest of the warm years in the past. And so if we don't plan for that, we're going to be missing the ideal. And so I showed the climate lens there. This is a federally released plan from Infrastructure Canada, where it kind of acknowledges that we need to be we want to reduce greenhouse gas emissions down to that blue line, but we're still going to need to plan for climate change under either scenario. So how do you start adapting to climate change when the difference by the end of the century, between this business as usual and this very successful greenhouse gas reduction, the difference is so large, the 6 degrees versus 2 degrees? One of the things we usually do is focus on the middle of the century. So by the 2050s here, there's not nearly as much of a difference between these different scenarios, in particular between the sort of red and yellow lines, the yellow being sort of in between. But one thing is clear, that anything in this even the blue line here by the middle of the century is quite a bit different from historical conditions. So I'm just showing here the BC Building Code. Currently, all of the tables that are in the back of the building code, even though the code itself says we should take future climate into account, all of the data in the building code itself comes from these historical conditions. And you can see if you sort of go over to the right from those historical conditions, that's not the climate we're going to be experiencing. And although there's some uncertainty, we know that it's not going to be what was experienced in the past. Okay, so how do we deal with this? Do we even need future projections? So we have resilience in the title of today, of the summit. So I'm going to sort of play devil's advocate a little bit here and say, well, do we even need these future projections? What's really important is to understand the place. And so what I'm showing here for the example of water supply, if you have a snow-dominated water supply area on the right, and then is that on your right? Yes. And then a rainfall-dominated water supply area on the left, you don't necessarily need detailed projections of future climate to know that with warming, this basin on the right that depends on snowpack and snow melting, snow accumulating during the winter and then melting in the spring, it kind of depends on that snowpack, like Metro Vancouver, for its water supply, whereas a basin like that one on the left, if it's rain-dominated, like Victoria, for example, we don't depend on snowpack, so we don't have that kind of vulnerability. So you can become more resilient to climate change without projections. Often I pose this as a question, in the interest of time, I'm not going to do that, but I pose this as a question to an audience. Do we really need projections or not? Can we just become more resilient by thinking about what our vulnerabilities are? And usually it's about half and half, and then someone will say, why do I have to pick between these two things? This is a false dichotomy. It's not an either or. So that's what under the premise of that looking at the future projections can help you plan and help you become more resilient, I'm going to dive into the promised maps. And so here, we'll start with snowpack. This is decrease in snowpack, and in the watershed boundaries for Metro Vancouver, you're looking at about a 60% decrease in snowpack by the middle of the century. So, and in one of you see a range there down at the bottom. In a particularly warm year, you might expect up to 70%. So you can imagine that, having the quantitative projections is useful because just planning for less snowpack in general versus planning for, can you imagine having a year where you only have 30% of the snowpack by April 1st? We're going to have to do something in terms of expanding water supply reservoir. And so a snippet of a couple of the kinds of impacts, longer growing seasons. So we're looking at, this doesn't cover exactly the Tsleil-Waututh territory. This is work for Vancouver Coastal Health. It's pretty close. We're missing a little bit of the northern part there. But on the left, we have growing season length. So this is how many days are in the growing season. Historically, averaged over the whole area shown here, it's 282 days historically. And you can see that obviously there's some regional variation there, the lower mainland sort of parts of the territory being warmer at lower elevation and having longer growing season. But we're looking at an increase of plus 44 days. So that's potentially good news. Although, along with such a dramatically changed growing season, it raises questions we don't really want to think about around what about important traditional species? Will the climate be suitable for all of those species in future? And in some cases, it may not be. The other aspect of temperature in terms of warming, hot days. So we have historically in this region, and again, there's some spatial variability there, but 17 days on average above 25 Celsius. And this is sort of about the temperature above which things start to get uncomfortable inside. We start turning the air conditioning on. And we're looking at an increase of 51, so more than tripling the number of days above 25 Celsius. So that's a big deal. You can think for buildings, for example, especially when you're thinking about the building envelope, heating and cooling demand. That's not something we want to ignore when we're constructing new buildings, even homes. And then so just a little bit on, so it's temperature, and then a little bit on precipitation. So precipitation in the dry season here is projected to get even drier. So this is about a 16% decrease in summer precipitation, and along with that comes similarly about 20% longer dry spells where you have periods with no rain at all in the summer. The flip side of that is, so drier when it's normally dry, wetter when it's normally wet. So throughout the rest of the seasons, fall, winter, and spring, increased precipitation. And this is, Stuart mentioned impacts of extremes. What we're looking at here on the left is the total amount of precipitation that you get in the sort of wettest days of the year. If you can imagine the kind of 8 wettest days of a year, how much precipitation falls on those days. And the projected change here is 25% increase in the amount of precipitation that falls on wet days. So that means extreme precipitation. When it rains, it pours, and it's going to be pouring more often, both of those things. So that's it for me. And I meant to mention that as you've noticed now, I've focused just on terrestrial impacts. We've got a couple of speakers on aquatic impacts next. But if you want to know more about the kind of climate data that is available, this is all on the terrestrial side of things, though. There's a great webinar you can watch here, and another one on adaptation funding. And I believe these slides will be shared afterwards, so you don't need to rush to write down the link there. And some other resources, I'm not going to walk through them again. They're just there for you to have if you're interested in more resources. Thank you.